Have you ever watched a car drive by? Perhaps you notice something peculiar. The wheels, those rapidly spinning circles, sometimes appear to slow down. They might even seem to stop. Then, most strangely, they can look like they are rotating backward. This happens even though the car is clearly moving forward. This fascinating trick of the eye is known as the car reverse illusion. It is also called the wagon wheel effect. Many people have witnessed this phenomenon. It is a common experience, yet it often leaves us puzzled. How can something moving forward appear to go in reverse? It's a delightful quirk of how our eyes and brain work together. This illusion is not a fault in your vision. It is not a problem with the car either. Instead, it is a beautiful example of how our brains process visual information. The world around us is constantly in motion. Our senses work tirelessly to capture this motion. But sometimes the information they gather can be ambiguous. The car reverse illusion highlights this ambiguity. It shows us that what we see is not always a direct recording of reality. Our perception is an active process. Our brain is constantly interpreting, guessing, and filling in the blanks. This process is usually incredibly accurate, but occasionally it leads to these captivating illusions. The illusion is most noticeable with spoked wheels. Think of the classic wheels on an old stagecoach in a Western movie, or consider the alloy wheels on a modern sports car. The spokes provide clear visual markers. These markers help our brain track the rotation. However, under certain conditions, this tracking system gets tricked. The speed of the rotation plays a crucial role. The way we perceive light and motion is also key. It is a dance between the physics of the spinning wheel and the biology of our perception. Understanding this illusion gives us a glimpse into the complex machinery of our minds. So let us embark on a journey to understand this visual puzzle. We will explore why your brain sometimes tells you a wheel is spinning backward. We will look at the science behind this effect. We will consider the psychology of how we perceive motion. It is a journey into the very nature of perception itself. The universe is full of wonders. Some of them are as close as the wheels on the car driving down your street. Prepare to have your mind gently bent. Let's unravel the mystery of the car reverse illusion together. It is a testament to the intricate ways our brains construct our reality. The car reverse illusion is not limited to just cars. You might have noticed it in other contexts as well. Think about airplane propellers as they start to spin, or consider helicopter rotors. As they speed up or slow down, they can exhibit the same backward motion. Even something as simple as a spinning fan in your home might trick your eyes. If the lighting conditions are just right, and the fan blades have distinct features, you might witness this effect. It is a surprisingly widespread phenomenon. It occurs whenever we observe rotating objects under specific conditions. The key factor is often the way we observe the motion. Sometimes it happens under natural sunlight. Other times it is more pronounced under artificial lighting. Streetlights, for example, or the lights in a workshop can make the illusion more apparent. This is because many artificial lights do not shine continuously, they flicker at a high frequency. This flickering, usually too fast for us to consciously notice, can interact with the spinning object. This interaction can create the perfect conditions for our brains to misinterpret the direction of rotation. The illusion is a product of sampling, much like taking snapshots. This effect has been known for a long time. Even before the advent of cars and movies, people might have noticed it. Perhaps they saw it in spinning water wheels or windmills. The name wagon wheel effect itself points to its historical observation. Imagine a speeding stagecoach in the Old West. Its large, spoked wheels would have been prime candidates for this illusion. Spectators might have marveled or been confused by the sight of wheels spinning the wrong way. It is a timeless quirk of human perception clashing with the physics of motion. Understanding that this illusion is common helps us appreciate it more. It is not a rare glitch in our visual system. Instead, it is a predictable outcome of how our brains are wired. The brain is always trying to make sense of the world with limited information. When it encounters rapidly rotating objects, it sometimes takes a best guess that turns out to be incorrect, yet fascinating. This shared experience connects us. It reminds us that we all perceive the world through a similar, sometimes fallible, biological lens. The universe presents these little puzzles for us to solve and marvel at. To understand the car reverse illusion, we need to think about how we see motion. Our eyes are not like video cameras that record a continuous flow of action. Instead, our visual system processes information in a series of snapshots. Think of it like a flip book. Each page in a flip book has a slightly different image. When you flip the pages quickly, you perceive smooth motion. Our brain does something similar with the information it receives from our eyes. It takes these individual frames of visual data and stitches them together to create the experience of movement. This process is remarkably efficient but not always perfect. The illusion happens because of the relationship between the speed of the wheel's rotation and the frame rate of our perception. If the wheel spokes move to a position very similar to where another spoke was in the previous snapshot, our brain can get confused. Imagine a wheel with 4 spokes. If, between one snapshot and the next, each spoke moves almost to the position previously occupied by the spoke ahead of it, our brain might interpret this as a small forward movement. This is the correct interpretation, but it gets more complex from here. However, if a spoke moves slightly the position of the next spoke, or if it moves a significant portion of a full rotation, things change. Let's say a spoke moves to a position that is just where the spoke was in the last snapshot. Our brain, always looking for the simplest explanation for motion, might decide that the spoke has moved backward a small amount. It prefers to see a small backward movement rather than a large forward movement. This is because the new position is closer to the previous spoke's old position, but in the reverse direction of the actual spin. This sampling of motion is the core of the scientific explanation. It's not just our eyes, it's how our brain processes these discrete visual inputs. When the real movement is too fast for our brain to track perfectly from one frame to the next, it can choose an alternative, simpler motion. This alternative is often the illusory backward spin. The specific speed at which this occurs depends on the number of spokes on the wheel, and the effective frame rate of our visual processing, which can be influenced by factors like lighting. Our brain is a remarkable organ. It constantly works to build a coherent picture of the world around us. It takes in sensory information, sights, sounds, smells, and weaves it into our reality. When it comes to vision, the brain is particularly active. It doesn't just passively receive images, it actively interprets them. It fills in missing information, it makes predictions. This interpretive power is usually a great advantage. It allows us to navigate a complex world quickly and efficiently. But it is also the reason why visual illusions, like the car reverse illusion, can occur. In the case of the spinning wheel, the brain receives a series of snapshots. If the wheel is spinning fast, the position of the spokes changes significantly between each snapshot. The brain then faces a puzzle. Did the spoke move a long way forward, or did it move a short way backward to reach its new perceived position? The brain often opts for the path of least apparent motion. If moving a short distance backward seems like a simpler explanation for the new position of the spoke, that is what the brain will perceive. It's a shortcut, a best guess. This process is happening unconsciously. You do not decide to see the wheel spinning backward. Your brain makes that decision for you based on the available visual data. It is trying to create the most plausible and least energetically expensive interpretation of motion. A large, rapid jump forward might seem less likely to the brain than a small, slight backward shift. This is especially true if the new position of a spoke is very close to where a different spoke was just a moment before, but slightly behind its expected forward trajectory. So, the car reverse illusion is a testament to the brain's role as an active interpreter, not just a passive receiver. It highlights that our perception is a construction. It is built from the raw data of our senses, but it is shaped by the brain's rules and assumptions. These rules are generally very effective. They help us make sense of a dynamic world. But sometimes, under specific circumstances like a rapidly spinning spoked wheel, these rules can lead to fascinating misinterpretations. It is a beautiful example of the brain's constant effort to make sense of incomplete information. Alright, so here we are in section 5, the phi phenomenon, which is often referred to as the magic of apparent motion. It's a key psychological principle that helps explain the car reverse illusion. This intriguing concept was first described by psychologist Max Wertheimer way back in the early 20th century. Now, the phi phenomenon is, well, it's essentially the optical illusion of perceiving continuous motion between separate objects viewed rapidly in succession. Imagine, if you will, two lights placed side by side. If one light blinks on and then off, and then the second light blinks on and then off, and this sequence is repeated quickly enough, you won't see two separate flashing lights. Instead, you'll perceive a single light moving back and forth between the two positions. This is precisely what happens with the spokes of a spinning wheel. Each spoke acts like one of the lights in the phi phenomenon experiment. As the wheel rotates, the brain receives a sequence of images of the spokes in different positions. If the speed is just right, the brain connects the image of one spoke in one position with the image of the next spoke, or even the same spoke after a near full rotation, in a slightly different position. It then perceives this as movement. The brain essentially fills in the motion between these discrete visual inputs, creating a smooth perception of rotation. Now, the car reverse illusion occurs when this filling in process goes a bit awry. If spoke A moves to a new position, and spoke B, which was behind spoke A, is now very close to where spoke A was, but slightly offset in the backward direction, the brain might link the new position of spoke A to the old position of spoke A by inferring a small backward jump, or it might link the previous position of spoke A to the current position of spoke B, interpreting it as a small forward or backward movement depending on the exact alignment and speed. The brain, you see, seeks the most economical explanation for the change in the visual scene. The phi phenomenon demonstrates that our perception of motion is not always a direct reflection of physical reality. It's more of a constructed experience. Our brain takes these discrete sensory inputs and actively organizes them into a meaningful whole. When the inputs are ambiguous, as with a rapidly spinning wheel, the brain can construct an interpretation that, while logical from its perspective, doesn't quite match the actual physical movement. This is the magic and mystery of apparent motion, a fundamental aspect of how we experience our visual world. It shows the brain's powerful ability to create coherence. Section 6. Stroboscopic effects, when light plays tricks. The car reverse illusion is closely related to something called the stroboscopic effect. This effect occurs when a moving object is viewed under light that is not continuous but instead flashes on and off. A strobe light is the most obvious example of this. If you have ever been to a dance club with strobe lights, you have seen the stroboscopic effect in action. Dancers appear to move in a series of jerky, isolated poses. Their movements can even seem to slow down or freeze. This happens because you are only seeing the dancers illuminated during the brief flashes of the strobe light. Now, how does this relate to car wheels? While natural sunlight is continuous, many artificial light sources are not. Fluorescent lights, LED lights, and even some types of street lights actually flicker very rapidly. This flickering is usually too fast for our eyes to consciously detect as individual flashes. However, this rapid on and off cycle of light can act like a natural strobe light. When a wheel is spinning under such flickering light, our eyes only capture images of the wheel during those brief moments when the light is on. We are essentially seeing a series of still frames of the wheel. If the frequency of the light's flicker aligns in a particular way with the speed of the wheel's rotation, the illusion can become very pronounced. For example, if a spoke moves to the exact same position or the position of an adjacent spoke each time the light flashes, the wheel might appear to be stationary. If it moves slightly less than a full spoke-to-spoke distance between flashes, it might appear to move slowly forward. And critically, if it moves slightly more than a full spoke-to-spoke distance, such that it appears closer to the previous spoke's last illuminated position, it can seem to move backward. So the stroboscopic effect, whether from an actual strobe light or the subtle flicker of everyday artificial lighting, plays a significant role. It enhances the snapshot nature of our visual input. It provides discrete frames for our brain to interpret or misinterpret. The interplay between the wheel's speed, the number of spokes, and the frequency of the light source creates the conditions for this captivating illusion. It is another layer to understanding why our perception can sometimes diverge so wonderfully from physical reality. The universe, even in mundane lighting, offers up these visual puzzles. Section 7. Real-world illusions from silver screens to whirring blades. The car reverse illusion or wagon wheel effect is not just something you see on the street. It has famously appeared in movies for decades. In old Western films, as stagecoaches raced across the plains, their wheels often appeared to spin backward. This was not an intentional special effect, it was a natural consequence of how movies are made. Traditional film cameras capture motion as a series of still frames, typically 24 frames per second. If the wagon wheel rotated at a certain speed relative to this frame rate, the illusion would inevitably appear on screen. This cinematic appearance helped popularize the illusion. Audiences would see it and wonder. It became a well-known, if not always understood, visual quirk of filmmaking. The same principle applies to footage of airplane propellers or helicopter rotors in films or on television. If the rotation speed of the blades aligns with the camera's frame rate in a specific way, the blades can appear to slow down, stop, or even rotate backward. This is the stroboscopic effect in action, mediated by the camera's frame rate instead of flickering light. It's the same fundamental principle at play. Beyond entertainment, understanding this effect can be important in some technical fields. For instance, in industrial settings, workers might observe rotating machinery. If the lighting conditions produce a stroboscopic effect, a rapidly spinning part could appear stationary or slow-moving. This could be dangerous if a worker mistakenly believes the machinery is not operating at full speed. Therefore, awareness of this illusion and ensuring appropriate, continuous lighting in such environments can be a safety consideration. The universe's tricks can have real-world consequences. Even musicians can experience a version of this. If a guitarist rapidly plucks a string, under certain lighting, the vibrating string can appear to form unusual stationary patterns. This is again due to the interplay of rapid motion and the sampling of that motion by our visual system, potentially aided by flickering light. The car reverse illusion is just one specific manifestation of a broader set of phenomena related to how we perceive rapid periodic motion. It reminds us that our senses are tools, and like any tool, they have their operational limits and quirks. Section 8. The alias of speed, why wheels seem to reverse. So, why exactly does the wheel appear to spin backward and not just in a confused, jerky manner? The answer lies in a concept called aliasing. In signal processing, aliasing occurs when a signal is sampled at a rate that is too slow to capture its true frequency. This results in the signal being misinterpreted as having a lower frequency, or even a different direction in the case of rotational motion. Our visual system, when observing a fast-spinning wheel, is essentially sampling the wheel's position at discrete moments in time. Imagine the spokes of a wheel are like points on a clock face. If a spoke moves from the 12 o'clock position to the 1 o'clock position between one snapshot and the next, our brain correctly perceives a forward motion. But what if the spoke moves much faster? Suppose in that same interval it moves from 12 o'clock all the way around to the 11 o'clock position. Our brain, seeking the simplest explanation, might not see the long journey forward to 11 o'clock. Instead, it might interpret the spoke's new position at 11 o'clock as a small backward movement from 12 o'clock. This is because the 11 o'clock position is closer to the original 12 o'clock position if you consider a short backward rotation compared to a nearly full forward rotation. The brain is, in a sense, fooled by this ambiguity. The true high speed of the forward rotation is aliased into a perceived slow backward rotation. The actual rapid forward motion is misinterpreted because its frequency is too high for our visual system's sampling rate, or the camera's frame rate, or the flicker of a light source, to accurately capture. The true motion is masked. This aliasing effect is the mathematical and perceptual reason behind the backward spin. It is not just a random confusion, there is a specific relationship between the actual speed, the number of spokes, and the sampling rate that determines when the forward motion will be perceived correctly, when it will appear stationary, and when it will appear to reverse. The universe operates by physical laws, and our perception, while complex, also follows certain rules. The car reverse illusion is where these rules of physics and perception intersect in a particularly intriguing way. Section 9. Conclusion: the astonishing universe within our minds. The car reverse illusion, that curious trick of spinning wheels, offers us more than just a moment of visual surprise. It provides a profound insight into the workings of our own minds. It reminds us that perception is not a passive window onto an objective reality. Instead, it is an active, constructive process. Our brains are constantly interpreting, inferring, and even guessing, all to build a coherent and useful model of the world around us. This model is usually incredibly accurate and allows us to navigate our lives. But sometimes, its shortcuts and assumptions lead to these wonderful illusions. We have seen that this illusion arises from the way our visual system samples motion, like taking a series of rapid snapshots. When the speed of rotation interacts with this sampling rate, our brain, seeking the simplest explanation for the changes it observes, can be tricked. Principles like the phi phenomenon show how we perceive motion even from discrete stimuli. The stroboscopic effect, caused by flickering lights or the frame rates of cameras, can enhance this illusion, creating the conditions for our brains to misinterpret the direction of spin due to aliasing. This is not a flaw in our design. It is a feature of a highly efficient processing system that has evolved to deal with a complex and dynamic environment. The brain's ability to fill in gaps and make rapid judgments is essential for survival. Illusions like the wagon wheel effect are simply fascinating byproducts of this sophisticated system. They are moments when we get to peek behind the curtain and see the machinery of perception at work. They highlight the boundary between the physical world and our subjective experience of it. So the next time you see a car's wheels appearing to spin backward, or notice a helicopter's rotors behaving strangely on film, take a moment to appreciate it. You are witnessing a beautiful interplay of physics, biology, and psychology. You are experiencing the universe not just outside you but also the astonishing universe within your own head. The cosmos is filled with wonders, from the grandest galaxies to the intricate neural pathways that allow you to perceive a simple spinning wheel. And sometimes understanding how we are fooled can be just as enlightening as understanding the straightforward truth. It is all part of the grand cosmic tapestry.